So, welcome everybody to this third episode of ML Papers, Learning from Imbalanced Data. Now, this paper is quite lengthy, 22 pages, if I remember correctly. So, it is not something we can cover in completion in 1 hour. But these are the main sections. The first part, that's something it's some background I need to take you through before we jump into the sections of this paper. But the sections are sampling methods for imbalanced learning. That's today's session. For the other sections, cost-sensitive methods for balanced learning, kernel-based methods, and the additional methods that are covered in this paper, they will either be separate. They will definitely be either separate sessions, live sessions, or I will supplement this session with separate video recordings because it's quite, like I said, it's a lengthy paper. So this entire session is actually for section 3 of this paper. Now that's it for the slides. I'm actually going to take you to VS Code to take you through the markdown notes. So let's begin. Section 2 of this paper talks about the nature of the problem. What is this paper about? What is it trying to address? If you look at this picture here, this scatter plot, you can see that we have a lot of these blue circles, which we call observations. Again, in statistics, the word observation means something that has been recorded, something that has been observed in reality, and it has been recorded. Financial transaction, maybe an accident, sales. So these are things that have actually happened. In this particular data set, we have observations that fall into two classes. You can see here, however, that we have a severe underrepresentation for one of the classes. So the observations in blue we will call members or instances or observations of the majority class. And the stars here, these purple stars, these are the observations that fall into the minority class. Before I go any further, let me point out that this paper uses words like instances and examples. I prefer to use the word observation because example and instance, these are not actually statistical terminology, or for that matter, machine learning terminology. So in the paper where they say example or instance, I'm going to use the word observation. Observation for things that actually happened and estimates for data that is generated artificially, which is part of what this paper talks about. Okay, so again, we have a data set here with a majority class and a minority class, but that's not all. This data set is a data set that is imbalanced. Now, some imbalanced data is not a problem. Okay, it could be 60% majority class, 40% minority class, 80% majority class, 20% minority class. In such instances, you can still learn the parameters of the data and the model can still perform very well with respect to its accuracy. This paper talks about highly or severely skewed data. What do we mean by severe? We mean when the ratio of the majority to minority is 100 to 1 or more. So for every one minority class observation, there is 100 observations for the majority class. So 100 to 1, 1000 to 1 or more. So this is severely skewed. This kind of data set is problematic. When you have a situation like this and the machine learning model learns from the training data set, it does very well when it comes to the majority class, but the minority class members, the minority class observations are so overwhelmed that the model cannot even identify them, cannot properly classify them. So we have a situation where we have 100% accuracy for the majority class, but only 5% accuracy for the minority class, meaning they are constantly being misclassified as being members of the majority class. This is very problematic, depending on the problem. Uh, First of all, where and when do we come across such highly or severely imbalanced data? In finance, for example, in fraud, in uh, healthcare, for diagnosing uh, high risk but also uh, unlikely diseases, cancers, and that kind of thing, fatal or very problematic diseases. So they happen infrequently, but when they do, they can cause disproportionate damage. So it is very risky to misclassify an observation of the minority class as being an instance, or excuse me, observation of the majority class when the consequences can be severe. So misclassification can be very problematic. I mean, if it's fraud and you uh, if you misclassify one transaction, it can literally shut down the entire operation, the bank or whatever the financial institution is, and incur incredibly large fines. So what this paper wants to do is come up with solutions, or it proposes solutions for very accurately classifying minority classes, and also it talks about metrics for uh, well, visually and empirically uh, determining the performance of the machine learning model. ROC analysis, by the way, is a big part of this. In the previous episode, we talked about how ROC analysis is, let's say, robust against imbalanced data. So it does well with balanced data and imbalanced data, which was not true for the precision recall curve. Okay, so this paper is very, let's say, comprehensive, and that's why it's quite lengthy. Now, I give you two examples of where imbalanced data can occur, but the examples I gave you were examples of intrinsic imbalanced data. Intrinsic means it's natural. Fraud doesn't happen frequently. Or let's say major fraudulent transactions that involve millions of dollars, or and there are scandals involved. They happen infrequently. They're very problematic, but they happen frequently. Same thing for very um, dangerous diseases. But then we also have extrinsic class imbalance. This can happen because of uh, a few different scenarios. I think I'll type them in later on. But when can extrinsic happen? For example, when there is a data entry mistake. Someone is recording data, but where they were supposed to type 10, they typed 100. Or there was a spelling mistake. So the data is unclear. Another example could be, let's say you are surveying supermarkets to see if they are, the section where they have poultry or dairy and everything is meant to be refrigerated. You want to make sure that these this supermarket branch, this Whole Foods branch, if you like, is keeping these goods at a suitable temperature. So not too high where they, and not too low, not too low. We don't want to damage the foods, okay? So we wanted to make sure when the customer buys that, they don't suffer from food poisoning or salmonella. So we sent someone from the municipality or the FDA or whatever the governmental department is responsible for doing such surveys to the supermarket, and they take note of the temperature. Now let's suppose I'm exaggerating, okay, just to make it to make you understand what I mean by extrinsic class imbalance. Let's say that particular day, the surveyor goes to the supermarket. There was some sort of snowstorm or tsunami or whatever, and the electricity grid of the entire town was damaged. So there was no electricity anywhere. But when the surveyor is taking a note of the temperature, it's unacceptable. Now, does that mean that supermarket is does not follow the regulation or is breaking the law? No, it's not their fault. It's the situation surrounding them. So that surveyor should revisit that day. Should reschedule. Okay. Now that obviously that's an exaggerated example, but it can happen where an observation is affected by uh, unforeseen circumstances, which needs to be corrected. We are not talking about that extrinsic situation because these could be fixed. But when it's intrinsic, like fraud or disease detection, not really. So because imbalance is its nature, it's part of it's part of the phenomena. It cannot be avoided. So how do we go about dealing with such a problem? Let me jump to section 3. Okay. Now I've left here some math notation and I defined what the symbols mean for later reference. We'll come back to the section if needed. But this section is mainly about sampling, and I'll give you some background about statistical sampling and synthetically generating data. Sampling and synthetically generating data. First, let's talk about sampling. And just in case you're not familiar, sampling means to randomly draw, uh, observations from the population, right? Again, statistics and by extension, machine learning is the science of making inferences about the population when you only have a sample, right? We will never be in a situation where we have all the data we need. So what we want to do is randomly sample from different classes to make sure we have good representation from all the different categories, and then from there we can talk about inference. Okay, so that's what sampling is about. This paper talks about combining machine learning with statistical techniques for cleverly sampling, and in some cases even artificially generating data, because there are some situations where there is no data from which you can draw samples. Fraud is an example. Disease is another one. There's just not enough of it occurring for you to draw samples. So how do we address imbalanced data? Again, here we have imbalanced data. Again, obviously the blue ones represent the majority class, the pink or whatever, what is this, magenta, whatever that color is. It's the minority class. To undersample is to intentionally discard randomly some of the members of the majority class. So you kind of have a 50-50, to kind of offset the imbalance. To oversample means to go after the minority, to go after data from the minority class and draw or sample more of them. So again, you manage this imbalance. Now, it would be great if you could oversample. Like I said, there are some situations that intrinsically have class imbalances. You cannot. There is no data from which you could draw samples. On the other hand, undersampling, in undersampling, you're discarding data. You are discarding valuable information. So, in short, undersampling can cause underfitting, whereby the model is not able to generalize. There's just not enough examples. Oversampling can also lead to overfitting. In both cases, the model is not doing a good job of generalizing, which means that after we feed this modified training data set and we present to it a test data set or actual data from the real world, it will fail to accurately classify data. So this is random sampling, random oversampling or random undersampling. We want to be a little more particular about how we do it. So not completely randomly. Now, in statistics, we have four types of sampling. Not machine learning, just statistics as a science. We have these four main categories, and they are better in descending order. So, for example, the first one is sample random sampling. Imagine you have like a bowl, and you reach in, you give it a nice mix, and you draw something from it, like a piece of paper or a ticket number, like in a lottery. It's good, but we can do better. Then there is systematic sampling. Let's say we want to, again, going back to that whole municipality, want to make sure that the supermarkets in the area are doing a good job with food and stuff. It's too time consuming and expensive to go to every single grocery or supermarket, Whole Foods, and survey them. What you can do is go to every second or every third supermarket. This is one form of systematic sampling. Better, but we can do better still, right? Then we have cluster sampling. Cluster sampling is where you basically evenly divide your observations. And if you look at this picture here, when you divide your observations into clusters, the expectation is that every cluster will have at least a member, or will have a good mix of every class. So here we only have two classes, right? The blue class and the red class. And this is more uh, controlled. And then we have stratified. This is the most effective, but conversely the most expensive, because what you have to do is you have to identify the different strata, the different classes of the observations, and then from each strata sample a data set, sample examples, sample observations. Okay? But again, this goes back to the initial problem. There are phenomena that are intrinsically imbalanced. So even if you do stratified sampling, fine, you will still have a class imbalance. So let's see what we can do. I will move now down to section 3.1.2 of the paper, which talks about informed undersampling. In informed undersampling, we will use an ensemble machine learning model or ensemble machine learning models. Ensemble, by the way, means that we use a combination of machine learning models, like a random forest. A random forest uses different decision trees, of different heights and different depths to learn features, to learn the parameters of the features of the data set. Okay, that's what an ensemble machine learning model is. Two examples to which this paper refers are the easy ensemble and balanced cascade machine learning models. Here's what they do, and they're used together. The easy ensemble machine learning model is there to identify the majority class. So imagine you have a scatter plot of all the observations, but you do not know which one is minority, which one is which one is majority, which one is minority. And you can use and there are of course other unsupervised machine learning models with which you can find different clusters. There's k-means, there is nearest neighbor, principal component analysis, right? There are you can look up cheat sheets to look up the different unsupervised machine learning models, but there are different plenty of effective techniques for finding the majority and minority class. So that's what easy ensemble is used for. Then we have balanced cascade. Balanced cascade is going to produce a series of classifiers. Here's why, and here's the role of each classifier. Suppose we have a situation like this. Okay, the blue observations are the majority class, the purple ones are the minority class. What was it called? The cascade, balanced cascade will do is it will repeatedly take, let's say, subsets of the majority class. So for example, it will take this part, including the minority classes, and then again this part with the minority classes, and then again this part with the minority classes. The idea here is to generate multiple subsets of the majority class whose size is equivalent to the minority class. In other words, what we are going to do is produce several subsets of this data with majority 1, minority 1, majority 1, minority 1, majority 2, majority 3, majority 4, and all of these subsets of the majority class are equal in size to the minority class. And what we will do is for each of these subsets, we will have a classifier. So we will have, let me show you what I mean. If I type it down, maybe it might be clear. So let's say we have data set like this. Yes, we have 1, 1, 1, 1, 1. These are members of the majority class, and then we have 2 and 2. Okay, what we will do is produce subsets like so. So for example, we can have 1, 1 and 2, 2. Okay, so for example, the first 2 observations. Then we will do this again with these 2. Okay, and then we will do it again for these 2. You see what I mean? So now we have 3 subsets. And you can see here, all 3 subsets are balanced. And to each subset, we will produce a classifier. The paper represents a classifier as H. They call it hypothesis, but what they mean is the classifier. So this would be classifier 1, and this would be classifier 2, and then this will be classifier 3. And then so this is these subsets are easier to learn from for these classifiers. So what will happen then is basically, long story short, is we will combine the parameters of these classifiers together to produce the final result. This is what we mean by cascading, balanced cascade. So the data set, the subsets are balanced. Then we have a series of classifiers, and then we will cascade them to produce the final classifier. That's the idea. So let's return back to the notes. Okay. And again, I've also labeled the syntax for you. So we have H sub i's. These represent the hypothesis, which are actually classifiers. The entire paper uses E to represent sample data. So wherever you see E, we're talking about resamples. So oversampled or undersampled, we will use E. And the samples, like I said, must be the same size as the members of the set of minority observations. Okay, and then what we're also going to do is this. Every time something else that I forgot to point out. Every time we produce a classifier, yes, we are going to remove the observations from which we have already learned. So for example, in the first subset, we learned about the first 2, so we will eliminate them. In the second subset, we learned from the first 2, we will eliminate them. And then that is also another data set that we can generate, because we will recursive, or let's say we will iteratively do this because we have already learned from the data set, so it's redundant to keep them in there. Okay, let's look at the other techniques. We will go down to section 3.3. Yes, synthetic sampling. Synthetic sampling and generating data. So this is where we'll talk about not just sampling, but actually producing new data sets. So this is using a machine learning model called SMOT, which, again, what does it stand for? And let me look at my notes here. I keep forgetting. SMOT stands for Synthetic Minority Oversampling Technique. Let me include it here in the paper for you. So if I go to SMOT, this is a paper on its own, obviously, and it's also included in the notes. So yeah, synthetic minority oversampling. That's that's the acronym. And here's the idea. This technique produces artificial data. And this is, by the way, a vector. The paper does not use a bold X or an arrow on top of it, but you have to be careful because this is actually a feature vector. And it's labeled as X sub nu. And where necessary, the minority class, for the minority class, observations will be generated. But I should be careful not to use the word observation because these are not actual data, these are synthetically created. So we will say estimates are created. And this particular technique combines the majority class oversampling together with SMOTE to produce new minority classes. So let me take you to the notation to talk about this, and I'll return to the figure to explain what's going on. So we have x sub I, which is some particular observation, and we have the hat over the x, which is a particular neighbor of this feature. Let me stop here and take you back to the paper to tell you what I mean. So here we have, let's say, x sub I, and you can see it is a member of the minority class. So we have all of these circles, which are members of the majority, and then we have the stars, which are members of the minority class. What we want to do is augment. We cannot oversample because there is no data from which we can sample, so we have to synthetically generate the data set. Here's how we will do it. We will take one particular neighbor, for example, this one, this hat x sub I. And then what we will do is subtract the distance between the two and then multiply this difference by some number between 0 and 1, a real number between 0 and 1. It's supposed to be random. And then offset this generated data somewhere along this distance, so somewhere in this vicinity, like within that vicinity. For example, somewhere here, if you can see this tiny square, that's where this synthetically generated has been inserted. And we will do this repeatedly as much as required so that we can increase artificially the size of the minority class. Okay? So if I return here, this is the formula that they use. So here we have one particular neighbor, and we will subtract it from the feature. By the way, these are vectors, so we can perform arithmetic operations on vectors. We can do addition, subtraction, dot product. And then this delta represents some random number between 0 and 1. Okay, because the feature should be randomly different. It has to, if you go back to episode 1, I talk about feature vectors in case any of you are familiar. You can revisit ML Papers episode 1 and you can see an example of what a feature vector is. And then this addition part is to offset it. So once we have created a synthetic feature vector, we will offset it in close proximity to this particular observation. So it will be surrounded by synthetically generated, like siblings or members of its own class. And of course, since this is similar to k-means cluster, we use the k-means, the Euclidean distance formula to calculate. Again, this is also talked about in the previous paper. So someone asks, does SMOTE only work with features that are numerical? No. We are not talking about the original features. We're talking about vector representations of the features. So this can work for words, it can work for sound, it can work for text. If you go, like I said, if you visit ML Papers, I will show you how to. I'll explain how we can go from words, text, but these are what we call modals or modals. We in machine learning, everything has to be numerical for the machine learning model. Machine learning models are ultimately mathematical operations. So that implies everything has to be numerical. So whether it's text or audio or whatever, it has to be converted to numbers somehow. But it's a different topic altogether, which is why I suggest you have a look at that. Okay, so feature vectors, this can work for any kind of problem, any kind of modality. Okay? Now, there is a problem with this approach. It's great, so we have a effective way of artificially oversampling for the minority class, but there's a problem. And this is where section 3.14 we talk about the problem. The problem is this. SMOTE does not care about neighboring classes. So if I scroll back up here, Here's one identified minority class. But there could be other minority classes in this section or even neighboring sections. The problem is that because smote is indifferent to the neighboring classes, overlapping can occur, meaning it can do smote for a member of this class and then go to a very close neighbor and smote for that class, and then both of these have artificially generated neighbors. And again, this can be problematic. So in the subsequent section, we're going to be a little more granular. So we don't indifferently generate synthetic data, we generate it where necessary. And here's how we can define where is necessary and where is not necessary. There is another paper that takes the smote idea and develops it, called borderline smote. Okay, in borderline smote, here's the situation. First, we will find, like before, a nearest neighbor for a member of the minority class. Okay. Then we are going to, if I remember correctly, yes, find the size. Let me actually double check the syntax here, because this is, so this S subscript I m minus n is the set of nearest neighbors. So what we want to do is produce a set. That's what this is the cap. This is the intersection symbol. We will take the intersection of the nearest neighbors and members of the majority class. Basically, we want to know how many neighbors of this minority observation are members of the majority class. Why? Basically, if a particular observation from the minority class is surrounded disproportionately by members of the majority class, then this set is considered, this particular observation falls into a set called the danger set, because they are underrepresented. Okay, so for example, if you see for observation A, it is surrounded by two members of the minority class. This is A. That's one member of minority class. That's another member of the minority class. Whereas it is surrounded by four members of the majority class. So there's 1, 2, 3, and 4. Because this instance is in danger, so to speak, it makes sense to artificially or synthetically generate neighbors for this data set. And that's what this tiny square represents here. Whereas if you look at for observation B, you can see it is, it's like in its own neighborhood. It is in a good place. It is surrounded by plenty or adequate members of its own class. So because it's safe, there is no need to synthetically generate data. Why is this good? Well, look here. There is no overlapping. We are not introducing complexity to the data. So as opposed to generating synthetic data everywhere there's a minority class, we will only do it if that particular minority class is surrounded by majority classes. And then there is the noise class, where, here we have, I don't know why they're using circles here, but it says, so if the number of minority classes is 6 and there is no member of the majority class, then this is just noise. We can just leave that alone. Okay, so this is how we take smote to the next level. Okay. Now, that's borderline smote. Then also related to this section is the ADSIN, which stands for adaptive synthetic sampling. Adaptive synthetic sampling, if I remember, let me see if I can remember what this is about. Okay, actually, yes. What I meant to say is they work together. Borderline smote and adaptive synthetic sampling are used together. So where smote generates every data, smote is only. So borderline smote is for finding the borders to identify which set is danger, which set is safe, which set is noise. And adaptive synthetic sampling is for producing the selected number of synthetically generated data. Question: my understanding is that in C class, the star samples may be noise in fact. The C in class. Oh, yes, that's correct. Yes, that is correct. Okay, let's move on. Then we have section 3.5, where we, in addition to sampling, we also clean the data. So let's see how this is done. Let me look at the notes here. Yeah, so here we have these things called tomic links. Tomic is the name of the author, and this is actually not a very recent paper. It's an older paper, but it's a interesting technique nonetheless. So we have a pair of observations where x sub I is a member of the minority class, x sub j, this was meant to be j, excuse my typo, x sub j is a member of the majority class. And here's what we are looking for. So in figure 5a, we have the original set distribution. And let me make sure I did not leave out a detail because I have to use my memory here. Let me actually see if I can remember what the distances were for. So if here we have the distance, so d here represents distance function, distance between the minority class and the neighbor, and the majority class and the neighbor. If the distance is not unequal, then what happens is we form tomic links. So let me see here. We have so if you see here, we have these observations that are too close to members of the majority class. And what happens is they are forming these tomic links. Okay, so we use the Euclidean distance to measure the distance, and if the distance is not substantial enough, we form these links, and when those links form, we will know the location of those links, and we can remove members of the majority class. So this is a clever undersampling technique. Okay. I meant to put undersampling in here, but maybe I'll update the text. But yeah, this is an undersampling text. We are removing members of the majority class, and we remove the members not randomly, like I stated in the first part of this talk, but we will remove members of the majority class when they surround members of the minority class, like forming a chokehold or something. So more clever techniques for undersampling. Okay, let's carry on. Then we have cluster-based sampling method. Now this one also has two parts. So long story short, here's what's going to happen, and I'll take you through the details. We have this original data set, and we don't have a binary class situation. We have multiple classes. We have multiple minority classes. And what we want to do is synthetically increase the number of observations, or I should say oversample for each minority class. So you can see we have a lot more instances in this figure. So let's see what's going to happen. First, we are going to use a unsupervised model to find the clusters of the dataset. Okay. So the paper refers to cluster-based oversampling, CBO for short, which combines k-means clustering and the oversampling technique. And here's the step. First, we will randomly sample from each cluster. Okay, so if the data is labeled, great. If the data is not labeled, there are unsupervised learning techniques for labeling the data. But first, we randomly draw from each cluster. That's what figure B is. So here, for example, we have 1, 2, 10, right? We have 10 members. What we do is we randomly sample from each class. So, for example, 3 from class B, 3 from class C sub D, another one for Why is this called seeds of the? Oh yeah, no, yeah. Sorry, this is yeah. So 3 members for class B, 3 members for class D, 3 members for class C, and so on. Okay, so we take a few examples from each class. Then what we want to do is find the centroid or the center of the cluster. So we know what the clusters are, but we don't know the center. We don't know the middle part of each cluster. To calculate the middle part of each cluster, the center of the cluster, we will start to reintroduce members of each class to the data set. Every time we do, we are going to recalculate the mean average. So for example, after we reintroduce this new observation, this is the new calculated, this delta sign. This is the new identified center. And the center keeps moving. So every time, for example, if the center is here and you add 2 more observations to the top, the mean will shift upwards, right? Because it has to be in the center of the cluster. Once we have identified all of this, if you see here, I don't know if you can see it clearly, but the mean has moved from here. Can you see this dotted triangle? To here. So the mean has shifted here as well. For the D class, the mean has moved from here to here. So we are going to readjust the centroid of each cluster. Once we have found the centroids of all the clusters, we will start to pool in more artificially generated data. So this is a combination of using k-means to find the centers of the cluster and then to artificially generate more observations. So now you're oversampling for every single minority class. And yeah, I think this is it for section 3.1. There's a 7th section which combines sampling and, if I remember, boosting algorithm. And in boosting, what we do, I guess that will be a supplementary section that I will include here. But in boosting, you have one classifier which learns the parameters and then will pass on the parameters that it has learned onto the next machine learning model. That's also a form of ensemble machine learning. Okay. So I managed to go through almost the entirety of section 3.1 in about 40 minutes. So maybe there was more time. Not enough time to talk about section 3.2. So 3.2 was cost-sensitive methods. And now for cost-sensitive method, this has a lot to do with classification metrics. Again, I highly recommend that you visit the recording of the previous episode. And a kernel, by the way, is a terminology from, what do we call it? Linear algebra. A kernel is also a basis function. Kernel methods in machine learning are functions that can do either 2 things. One, increase the dimensionality of the data, like in kernel regression. So if you have 1-dimensional data, you can actually turn it into 2-dimensional data. Or go the other way around, like in support vector machines or PCA, where you go from 3 dimensions or 4 dimensions down to 2 dimensions. So you're reducing dimensionality. So this paper also talks about kernel-based methods to learn from the data. Okay, because class imbalance is one problem. The dimensionality of the problem is the dimensionality of data adds another set of problems of its own. So for example, you can have a majority class and a minority class, but they can have a lot of features. So in other words, you can have a lot of dimensionality. That's also another thing you have to take into account. So not just the number of observations, but also the dimensionality of the observations. Question: I want to confirm these are references from Haibo. Yes, this exactly. So the author names are these, by the way. This is the original paper. So the authors are Haibo and Edwardo Garcia. So far I've taken you through sections 3.1. And in separate videos, I'll cover 3.2 and the other sections. Like I said, this is a very lengthy paper, lots of text. I actually prefer text with more math notation because they're more compact, but This is a very useful paper, and it does deserve multiple sessions on it. Okay, I'm not gonna actually browse anymore, but yeah, I'm just trying to show you the size of this paper. It's quite lengthy. Okay, and yeah, ROC analysis is covered here, but I suggest you watch that video before you jump into jump into the subsequent sections, because that will give you plenty of context and background. So while we have 10 minutes time, I want to open the session to any questions or comments that you have. And you're welcome to turn on your microphone, by the way. Any questions about what we've talked about today or any related concepts? Let me actually go through the chat, see if... Well, yes, this session is being recorded, and you will find the recording no later than Wednesday. If you have joined the Slack channel, you'll find the link there, also on the YouTube page. No questions? Everything was clear? You don't have questions at all? Okay, another question. No questions. Okay, while you think of... Yes, go ahead, please. How can you make sure that when you have... Good question. Now, there are two ways. One of them is to do it visually. Like here you can see in this picture, there is overlap. So the X and Y coordinates conflict. So how can you tell if this is members of the same class? Then, of course, there is the empirical way. So you can see this numerically. But something we haven't talked about is kernel regression. So again, when you have overlapping, another way to discern if these are to separate observations when they overlap is to increase the dimensionality, to go from 2D to 3D. So just think about this. If you have this scatter plot and it's two-dimensional, from this perspective, it looks like this minority class and the majority class have the same features. But if you were to add a third dimension, well, then you would have a 3D view. Like you could turn the plane around and you can see, oh no, there are features that separate them. That's the short answer. But this paper goes into more detail. More important than, not more important, but also importantly is not just the overlapping part, but the model's ability to classify one observation versus the next. And that's what 3.2 and section 4 in this paper are about. So after you train your data set, you also have to look at the test data set. And to evaluate the test data set, you have to look at the metrics, which include accuracy, precision, recall, F measure, and obviously the ROC analysis curve. So you have to check it during the training and the feature engineering part, but also after the when you look at the metrics of the machine learning model. Another question, this versus stratification, what is the oversampling benefit? For the minority class, oversampling means that you have more instances to learn from. Again, the purpose of machine learning is the ability to generalize. And we can only have a machine learning model that is capable of generalizing what it has seen enough examples from the different classes. So if you're talking about fraud, how many transactions happen daily in finance? Let's say we take one particular branch, one particular bank in a small country. There could be tens of thousands of transactions. And there could be only one fraudulent transaction. Let's say for the whole month. That one fraudulent transaction, by the way, most financial fraud transactions involve very large sums of money. So they happen infrequently, but when they happen, they are significant. We need to, if there's only one case of fraud, then if we want to rely on machine learning to classify fraud, then we're not going to have any luck, because the transaction will happen and we won't know about it. So we have to oversample. We have to produce more examples, either actually or artificially. Although, let me point out something. In finance, there are rules-based uh, ways for detecting fraud. So they don't 100% rely on statistics. They are actually hard rules. So, for example, if a bank account is, let's say, 6 months old, but and it has not received any deposits, or the deposits are infrequent, and then suddenly it receives, let's say, $10 million in sum, that's instantaneously fraud. There is no need for machine learning for that. So, but again, that is a more like fraud is an extreme case, but that is where that's a situation where oversampling can help. Another question: do you recommend R or Python for implementation of these sampling techniques? It depends. For obviously, Python has a larger community base. Uh, all the you know most powerful machine learning models that we know, deep learning in particular, are implemented in Python. So because of the size of the community and the accessibility of Python, Python is easy to learn, and you can work with on any IDE, and there are many cloud platforms where you can deploy or you can install the Python and runtime environment. For convenience, I would say Python. But if you want to go down into the statistics, like if you want to do like focus on the statistical part, then I would say R. But then again, they're very similar syntactically. So if you know Python, shouldn't be difficult for you to learn R, and vice versa. So you can use both actually. Another question asks, these are like pre-processing steps to turn imbalanced data into balanced in order to then use the standard machine learning models. Yes, so that first part is correct. Are there machine learning models that can handle imbalanced data sets directly? Well, actually, these are machine learning models. So, for example, if I take you down to section, I think, yeah, if I take you down to section 3.1 and 2, right? So, for the undersampling method, here we're talking about two machine learning models. So you would use them in combination, by the way. So there is easy ensemble, and then there is balanced cascade. So I don't know if there's one machine learning model that will take the data set and then produce the final data set. You could combine them. I mean, you can use transfer learning, or you can actually create a pipeline that has easy ensemble and balanced cascade and call it a day. But each technique has application in different scenarios. So you might have to be, it depends on the data set. It always depends on the data set. And then there is the situation with uh, a shift in distribution, which is part of ML operations. And that's a different scenario. But I don't think relying on one machine learning model to do everything is the way to go. Because, data is not uniform. And especially if we're talking about skewed data or severely imbalanced data, that will definitely be the case. Comment here. Here's an interesting article I read. Extreme rare event classification using autoencoders. Yeah, so I'm so far into my reading, I have not come across deep learning. But I guess where kernel methods are involved, deep learning would come into the picture. But that's also a good. Thank you for sharing that, by the way. I will include that in Slack, since I'm able to save this chat. One more minute left, so let me just talk about something separate. But if you have any questions, I'll be happy to answer them. Just one more thing before you leave. Another question from Gene Brookman: oversampling versus stratification. What is oversampling benefit? What is the difference? No, so. Oh, okay. I thought you meant stratified. Stratification is where you identify the strata, let's say the different classes of the data set. And it is not confined to oversampling. So you can have strata and then use undersampling, or you can have your strata and use oversampling. So stratification is about identifying the classes. So this is in the sampling stage. Oversampling, we can say, is part of the feature engineering stage. So oversampling comes after stratification. And I've already, I think I explained the benefit of oversampling, and is the difference in cost computation. Um, I guess if you're using unsupervised learning for stratification, I mean, it depends on the technique. It depends on the data and the technique. I cannot give you one short answer. Is there a way to pick proportional number of items from each strata? Yes, there is a way to do that. But all that's sampling. That's statistics, which I don't think I'll have time to get into. And would one use methods to enrich data or data on data streams? Enrich data on data streams. Adapt a model over time. Can you rephrase that question, please, Valentine? Yes. Oh, that's a very good question. If you have live data that is being fed live. Hmm. So imagine if we go back to fraud, we are being fed in real time uh, financial transactions. Well, you cannot synthetically generating data where, but the model has to be trained beforehand. Can you give me a scenario? Like describe a scenario. Yeah, see that's, by the way, I've recorded a session. It's not on the website yet, but it will be soon, on machine learning operations. So maybe have a look at that. Maybe because that is a 1 hour talk, and I don't want to open that discussion just yet. Rancy asks, from the experiments I've done, credit scoring and spam classification, SMOTE outperforms the undersampling. So is undersampling ever appropriate? SMOTE outperforms the undersampling. Is Well, yeah. I mean, if you have repeat instances, if you have a lot of data from a majority class and they're very similar. For example, a customer makes the same transaction again and again and again. You can do undersampling, especially if. By the way, in some cases, you may have very severely imbalanced data, and you can only increase artificially data to some extent. Like you cannot triple or quadruple the amount of synthetic data. Having imbalance is not impossible to deal with. We're talking about severely imbalanced data. So, if it's not so severe, or if I should say, if it's very severe, and you have too many repetition among of the majority class, yeah, you can do undersampling. Okay, you can keep asking, but let me just add this one last thing. For those of you who've seen the website before, this might be a new change. For those of you who have not seen this before, there are a number of uh, self-paced courses. You can see a preview, for example, in this course, Introduction to SQL. And I have a survey for you. Basically, there are going to be courses that go into advanced mathematics and more, and courses where mathematics and machine learning are taught together. I'll answer that question now, Cherry. So, for example, these three courses have already been done, but they will be the video library will be available in October. So it looks something like this. If I show you this one sample course, I mean, similar to other courses you have seen, course providers you've seen. You have your video playlist, and then you have the course material, exercises, snippets, what have you. Okay, so there are three courses that already exist. So there is linear mathematics, which covers these topics. You will learn linear algebra, abstract algebra, linear programming, and PC is a big part of this course, together with Python. And then there is statistics that goes into the major parts of mathematical statistics, including time series, Bayesian probability, combinatorics, hypothesis testing, right? Have a look at these later on. But these will be subscription based. What I want to do is I want to know what you are interested in. So what I've done is I've produced a survey. It's a short survey to know, what you are interested in, like why maybe, what are you looking out for? Are you looking to learn machine learning or use machine learning for finance or for engineering? And then if you are kind enough to fill out the survey, you will be entitled to 1 month free subscription to any of the courses that are available or will be available from October and onwards. Here's the link to the form. I will be very grateful if you, take the time to fill this out. Okay, so yeah, 1 month free for the entire course library. The notebooks, the videos, there will also be office hours like this. So every week I will have an office hour. You can watch the course, and then live, if you have any questions, I'll be here to answer them. And there are going to be other instructors involved from academia, from industry. So, exciting stuff are coming soon. Any other questions? Last questions before I wrap up the session. Remember. Let me once again give you the link to this Slack channel in case you haven't joined. Because any questions you have, if you want the slides, if you want the paper, by the way, someone talked about the paper. It's not freely available, so I'm going to have to see how I can share this with you. If you want any of the resources, this is where you want to be. This Slack channel. Let me give you this link. Invite people to big number. Copy the link. Okay. Oh, thank you very much, Valentine. Is this the paper? Super. Oh, very. Thank you for this. I'm going to keep it here, but I'll include in the Slack channel. So yes, like I said, for the remaining sections, I'm going to record separate videos. Do check out the YouTube channel. By the way, here's the link to the YouTube channel. Let me give you the YouTube channel, youtube.com, see big number. You know what YouTubers say, yeah? Like and subscribe. So if you subscribe, that would be also nice. But yes, join the Slack channel. I look forward to your discussions. There's obviously going to be more papers. By the way, one more thing. On Friday, we have 2 special guests from a company called Ahana. And Ahana is a company that manages the PrestoDB Foundation. PrestoDB is a SQL-based database platform developed by Meta, which is now open source. And it's used by companies like Uber, Facebook. And the people who maintain that platform are presenting on Friday. So if you want to learn about data engineering and SQL for analytics, this event, I highly recommend you attend. Okay, so do RSVP for this one. Okay, everyone? So either way, I'll make sure I give you the paper, hopefully with permission. But I will make sure I provide you with the paper. Okay, everyone? Thank you so much. Enjoy the rest of your day, and I hope to see you in the next session. For now, take care and bye-bye.